All right, everyone, we are back and we are going to do PID control, proportional integral derivative control. It's one of the most widely used control strategies, academic, industrial settings, very versatile, very simple, relatively, easy to implement. And basically, the controller will look like this. There's basically three terms. So one is just a simple gain, proportional. One is an integral. Look, you can see why it's integral because the transfer function is a 1 over s, and a derivative term because if you take the transfer function of this, it's just plus or times s, excuse me. This is the control structure, so the air signal is going to be passed through all of these blocks in parallel. So we can kind of see how the block diagram structure looks like. So again, it's summed and it produces that control command. And that's really how it works. And there's three tunable parameters. It's a very, very large parameter space, and it can be, people use this very unintuitively without a structured tuning method or physical insight. So it's PID is really, really used used commonly especially when you don't know what's the plant. Now that seems like heresy to us in this class because we need to understand what are the dynamics of that plant system. However, there's lots of different settings, especially in the HVAC world, process control loops, a lot of thermal, a lot of fluid systems where the plant dynamics are either not well understood or they are too complicated to model, or it is kind of unknown or hard to predict. So in that case, you can actually bypass that plant and basically implement a PID control and tune it, often empirically or heuristically, and you can still get acceptable performance. So it's a very, very, very common thing to use, but it's also one of these things where, because it's very common, people often treat it as a black box and they don't understand the implications of essentially what we're tuning here. Now, that's not going to be the case with you all in this course, but that's just some background on PID controllers, which you may have heard before. So how can we use a PID but still have some physical intuition? Let's go to our old friend, mass spring damper system. So we know this system, we know the terms. Let's build the first term, the P term. Let's do a proportional controller. So we're just going to set, for this Unity closed loop feedback system, this system here. Here's our plant. And we know we can determine essentially the poles of that closed loop system as such. And what you can do is, before we even actually go and look into a numerical answer, let's just look at what this is saying. We know we're overdamped if it's greater than, we're critically damped if it's equal to, if it's less than, we're going to be underdamped, right? But what's really happening in this system, and how does it change the behavior of the system? Well, we know that this is the natural frequency of this system. And so by adding that proportional control, adding that gain, if you increase K, P, our proportional controller, what's going to happen? Well, my natural frequency is going to increase. That's going to lead to faster oscillations. Conversely, though, if we also increase P, or KP, excuse me, or not conversely, but additionally, if we increase KP, we're also going to decrease the damping ratio. And we know if we decrease the damping ratio, we're going to get more oscillatory responses. Our settling time is going to be remained unchanged because, remember, this is will be constant because C and M are fixed essentially in this system, right? It's not affecting those parameters. So if we add that static gain, it's going to really influence the system's stiffness. So if I increase that proportional control, the complex plane is going to just move further up on the axis. Our omega n increases, damping ratio decreases, more oscillatory responses. The real part, this sigma, so basically this part is unaffected completely from here, right? So we're just changing that oscillatory response. We're not changing the location on the real axis of our poles. So we don't have an improvement in settling time. If you increase KP, you will increase essentially the control effort and larger control, signals. Proportional control will speed up the response, improve tracking, but increase oscillations, limited impact on that rate. So let's go ahead and actually do this with a numerical example because I think it's important. I'm going to open. Let's go ahead and let's open lecture 11. Here we go. And what we can do, I've kind of just put some critical functions in here. So let's do a P control. So I've got my G of S. I've got now my controller in here. We can look at our transfer function poles. There's 2 of them. We can see, and actually we can set it to crazy values. Let's just do 0 first. Let's do 1. So I can see right now, I am stable, right? My 2 poles are negative. As I increase my KP, look at the location on my x-axis never changes, but what I'm increasing is that y-axis value, and I'm getting more oscillations, right, in that response. At least that's what we should expect. We can also look at how we can actually set that system up. So, for example, I can do this. Whoops. This is my y of t. Here's our KP. And we can see as we increase, I'm getting more oscillations. See? More and more and more and more and more and more and more oscillations. Now, you saw I initially had that value from like minus 400. I can also make this system actually be unstable with KP, right? So you can actually see the system, I can make it unstable if I gave it a negative KP value. Now, is that really feasible? I mean, no, not really. But it's just good to see kind of mathematically. Remember, if you're just plugging in values, now negative might not be intuitive, but you can do the same thing with positive. So you can kind of see where I become that stable system. So you can actually see it's, if KP is minus 196, we're going to go basically unstable. And actually, let's go ahead and see that right here. I think it's always fun to watch, to see that transition. Negative, negative, it doesn't like that. So you can see here, we're lying just on that, for 198. We're lying on that 0 axis. Usually we're just stable here. Because it should be 0. Yeah, we have to kind of tune that. I wonder if it's actually 196. But there's basically a value where, yeah, we can become negative, and we can become unstable. I wonder what I always like the system response because that can really tell you something. So, for example, let's look at here, minus 196. Yeah, you can see we're still, but then if we go to 195, now at least we're starting to level off. It's still kind of meaningless, but now we kind of switch here. But anyways, you can kind of get the picture. So overdamped to underdamped, that's that transition. Again, we don't want to be non-negative. So for greater than that, we can kind of see essentially the response to that system. So those are our takeaways for a proportional controller. Now, what if we add a derivative control? Well, stay tuned next time for the next video, and we'll see you then. Thanks.